Hola, chaps. Let's learn. Hola, chaps. Mr. Turek here. This is for aerospace engineering. Yesterday, during our Google Meet, the students requested that I do a truss example, but only part of the class was there to see the solution. So I'm going to do that very same example again right now for the benefit of those of you who had missed it. It is just one triangle, and point A, we'll call that at the origin. Point B is 7 units to the right from point A, and point C, the altitude of this triangle, is 4 units to the right of A and 4 units up vertically. That's point C, so its coordinates in the Cartesian coordinate system would be 4, 4. Let's presume that the units are meters, and I'm going to apply a vertical load at point C with a magnitude of 100. Let's say that the units are newtons. All right, so let's get on with analyzing this simple, fun truss structure. I accidentally put a dot here. That is not a vertex. It's just one more mistake on my part. So there's only a single triangle. Vertex A is at the origin. B is at 7, 0. C is at 4, 4. I have a load being applied vertically downward at point C. Analyze this truss. Figure out all the reaction forces, and then go internal and calculate for each member. Is it under tension? Is it under compression? Is it neutral? And what is the magnitude of the force for each truss member? Go ahead and feel free to pause this at any time and just work out the solution, and then resume the tape, because here I am. I'm going to go do it now. All right. Step 1. The sum of all the vertical forces have to add up to 0. And so if I'm pushing down from above with a force of 100 newtons, then at A and at B, which is where the roller is located, I must be pushing up with a total of 100 newtons upward force. If this were an isosceles triangle, and it is not, then this vertical force would split evenly between the two piers or post supports at A and B. If the load were completely over point B, then all of the reaction force would be through B, and this would be 0 force upwards at that point. Similarly, if the load were completely over point A, then the load reaction force would be all at point A, and point B would have 0. So you should be able to realize that the magnitude of the forces exerted by these 2 points A and B is directly proportional to the distance horizontally from the load to each of these 2 points. And it's inverse to the distance. So the shorter the distance, the greater the fraction of the total load. Here, the distance, this is 0 out of 7, and it gets 100% of the load. If it were halfway, it would be 50% of the distance, and it would get 50% of the load. Each of these 2 points would exert an equal and upward force. The actual ratio is 4 to 7. So you could just very simply, this is what I'm doing, cheating, doing things quickly, right? I would say that 4/7 of the reaction force of 100 Newton total has to be going through point B, and 3/7 of the total reaction force of that 100 Newton load must be going through point A. So same calculations as yesterday. 4/7 of 100 works out to 57.1 newtons. That would be the greater fraction going upwards through B. So I'm going to draw a reaction force, and I know I should start doing this to some sort of scale. 57.1 newtons upwards through point B. Everything through A has to add up with B to a total of 100. So I get 42.9 newtons of reaction force acting through point A. And I'm not sure that you can actually see what I'm putting on the monitor screen very well, but there you go. Squint if you need to, right? That might help a little. All right, so there are no horizontal forces here, just that one vertical load. These two vertical reaction forces, they cancel. Zero horizontal forces, zero reaction forces. So I'm done doing the first part of the analysis. The first part is to calculate the magnitudes and directions of all the reaction forces acting through the pinned point, which is only able to have horizontal and vertical forces, and the roller, which is only able to have vertical forces. So we're done. Now it's time to go inside. My habit and style has been to start off directly above the roller, just because that's where my mind goes first to figure things out. As I look at this roller at point B, and I'll try to draw point B by itself now underneath here. So here's point B. I know that the reaction force going up through point B has a magnitude of 57.1 newtons. And I know point B isn't allowed to go anywhere. That's the whole idea of doing these static truss problems, that the sum of all the horizontal forces have to add up to zero, the sum of all the vertical forces have to add up to zero, and the sum of all the moments or torques about any arbitrary axis have to also add up to zero. Otherwise, your truss is not going to stay where it's supposed to stay. So if the roller is pushing up on point B with a force of 57.1 newtons, then what's going on? Can AB do anything about that? No, it cannot do anything about that because this is a horizontal truss member, but this is a vertical force. Forces in one direction are independent of forces in a perpendicular direction. And so therefore, the only truss member that can do anything to cancel this 57.1 newtons upward is truss BC, member BC. It must be pushing down. And of course, as a side effect, it's also pushing to the right because it is at a diagonal. It's not a vertical truss, it's a diagonal one. So the vertical component of its push downward on point B must be 57.1 newtons. And that will cancel out the reaction force going up through the roller through point B. Side effect, because of the geometry of the pin coordinates, it is directly proportional to the magnitudes of the vertical and horizontal components of the forces, because the forces are in the same direction as the truss members themselves. So if this truss member drops by 4 units for every 3 units that it goes to the right, then the same thing must be true about the magnitudes of the force vectors. It must have 4 units of force downward for every 3 units of force that it has horizontally. And therefore, it's just directly proportional. If the vertical component of the distance is 4 units and the horizontal component is 3 units, and if the vertical component of the force is 57.1 newtons, then the horizontal component of that force must be 3/4 of 57.1 newtons. So 3/4, which is 0.75, of 57 point, I'll call it 1/4 newtons, works out to 42.9 newtons. And I'm just going to add that as a little sketch here at point B and label that magnitude as 42.9 newtons. So this is a side effect of truss BC pushing down on B down and to the right. It has to push down to cancel the reaction force going up through the roller. Side effect, it must also be pushing B to the right with 3/4 of the vertical force. Now, I can use Pythagorean's theorem and calculate the magnitude of the force of truss member BC. I'm taking the square root of 57.14 squared plus the square root of 42, I should say plus 42.86 squared. And I end up with 71 point, call it 4 newtons is the magnitude of the force being exerted by truss member BC. C is pushing on B. You cannot push with a rope. You can pull with a rope, and you can use a rope for tension, a pulling force. So because this is a pushing force, this must be compression. And so the C's that I just wrote down right here doesn't represent vertex C. It means I'm identifying beam member BC as being under compression in the amount of 71.4 newtons. Boop, done with that one. Next, still looking at point B, I know that BC is pushing C to the right in the amount of 42.9 newtons. I have to stop that. There's only one member left acting on C, and that's member AB. Thank goodness it's a horizontal member, because 42.9 newtons is a horizontal force. So AB must be canceling 42.9 newtons. And if this 42.9 newtons from BC is pushing B to the right, then A must be pulling B to the left, woo, in the magnitude of 42.9 newtons. And it's pulling it, so I can use a rope. So AB is under tension, and the magnitude is 42.9 newtons. To finish this off, yesterday, I think late in the period, I went to point C next, but notice this. It's 4 units to get directly underneath point C. It's 4 units of altitude to get to point C. And so therefore, conceptually in your mind, since you love math so much, you should realize that this is a 45 degree, 90 degree right triangle. And from math class, you'd memorize the ratio of side hypotenuse for right triangle. 1, 1, square root of 2. Here, we have a vertical reaction force of 42.9 newtons. We also have a tension force of 42.9 newtons. Wow, that's not really a coincidence, because the two legs of this right triangle are equal in length. And so the vertical and horizontal components acting through A are equal in length. And the hypotenuse is the square root of 2 times longer than the length of any one side. So 1 square root of 2 is the ratio. So if I take 42.9 and I multiply that by the square root of 2, beep, 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 I end up with 60.7 newtons. Last question. So is this a compression force or is this a tension force? Is C pushing A down into the left, or is C pulling A up and to the right? So consider what's going on already. B is pulling A to the right. The ground is pushing A up. Now, AC can only do one of two things. It can either push A down and to the left, or it can pull A up and to the right. B is already pulling A to the right. The ground is already pushing A up to the up. So hopefully you realize logically, C must be pushing A down and to the left to cancel the ground pushing up and to cancel B pulling A. So it's pushing, not pulling. This is compression for member AC. Ta-da! If you want as a check, you could go visit point C and analyze what's going on. I'll try one last free body diagram for point C. I'm going to start off by reminding you that it has a load of 100 newtons acting through it. And unlike some earlier example where I forgot that, you're going to remember that. So here at point C, there's a load of 100 newtons. Members AC and BC together will have to be canceling that. So what's going on? If C is pushing A down and to the left with a horizontal component of 42.9 newtons and a vertical component of 42.9 newtons, then A must be pushing C up with a magnitude of 42.9 newtons and to the right with a magnitude of 42.9 newtons. If you like, these are the Newton's third law reaction forces to the force of C on A. For every action force, there is an equal and opposite reaction force. So if C is pushing A down and to the left, then A is pushing C up and to the right. 42 newtons up, 42.9 newtons to the right. Crude handwriting, but that's what I wrote. So 100 newtons of force, the load, 42.9 newtons of upward force caused by A, 42.9 newtons of horizontal force to the right, also caused by A. Now, let's add in the contribution from B. B is pushing C up and to the left. The magnitude that C is pushing up is 57.1 newtons. And I'll draw that to the right of the force of A on C. And I'll just draw it a little bit longer and say this is the force on C caused by B pushing on C. It is 57.1 newtons. Meanwhile, B has a horizontal component. C is pushing B down and to the right. We said it was pushing it to the right with a magnitude of 42.9 newtons. So, by Newton's third law, for every action force, there is an equal and opposite reaction force. If C is pushing B to the right, then B is pushing C to the left. And so I'm going to add to this free body diagram the force caused by B acting on C. It has a magnitude of 42.9 newtons. Now, add together all of these forces acting on point C. Hopefully clearly to you, but do I need to zoom in to show you clearly with my scribbly handwriting? 42.9 newtons to the right being pushed by A is canceled by 42.9 newtons to the left being pushed by B on point C. Horizontal forces add up to zero. Vertically, a load of 100 newtons down is being canceled by 42.9 newtons up caused by A plus 57.1 newtons up caused by B. These two together add up to 100 newtons, canceling the vertical forces, enabling you to master a career in engineering. Ciao.